I got these questions from different past papers, so the naming of the figure cannot be in line with the question number. So figure 3.1 shows a model of a wind turbine used to demonstrate the use of wind energy to generate electricity. The wind is blowing towards the middle as shown, so you can able to see this is the direction of the wind towards the turbine. So circular area swept out by turbine blades, that is there. Okay. In part A of this question, Roman 1, so the mass of air passing through the circular area swept out by the turbine blades each second is 7.5 kilogram. The kinetic energy of the air that passes through this circular area each second is 240 joules. Calculate the speed of the air. Now, this question is very direct. So we know that kinetic energy from our previous video, kinetic energy is given by a half times m times v squared. Now, the kinetic energy we have been given, that is 240 joules within 1 second. So 240 times a half times the mass, which is 7.5 times v squared. If we make v squared the subject of the formula, then this will be equal to 240. We multiply both sides by 2, so we'll get here 2. Then you divide both sides by 7.5. So this will be, that is 240 times 2 divided by 7.5, and that is 64. So v squared is 64, and that means v will be able to find the square root on both sides. The square root of 64 is 8. So into two significant figures, this will be 8.0 meters per second. And that will be awarded 3 marks for that. So this figure shows an aircraft on the deck of an aircraft carrier. The aircraft accelerates from rest along the deck. To take off, the aircraft has a speed of 75 meters per second. The mass of the aircraft is 9,500 kilograms. Calculate the kinetic energy of the aircraft at the takeoff. So same is that kinetic energy is given by a half mv squared. Always write the formula so that we can able to do, it become easier to substitute. So the value we've been given here already, there's speed v, and then the mass here is here. So we'll have a half times the mass, which is 9,500 kilogram, times speed, which is 75 meters per second. So when you square this, this is supposed to be squared. That is a half, which is 0.5 times 9,500 times 75 squared, and that is this gives me 26,718,750. Okay, into two significant figures, this will be 2.7. So this is 337. So this is 2.7 times 10 power 7 joules. So this is in sound form. If you're not sure of the sound form, you can give your answer as 2,700,000 joules. Same concept. Part B, on an aircraft carrier, a catapult provides an accelerating force on the aircraft. The catapult provides a constant force for a distance of 150 meters along the deck. Calculate the resultant force on the aircraft as it accelerates. Assume that all the kinetic energy at the takeoff is from the work done on the aircraft by the catapult. This question can be done in two ways. One which is very obvious is this, that work done, which is due to the kinetic energy, is given by the force times the distance that is covered. So the kinetic energy is this, and therefore the distance from here will be, the force that you're looking for will be given by 2.7 times 10 power 7 joules divided by the distance, that is 150 meters. So that is 2.7 times 10 power 7 divided by 150, and that is 180,000 newtons. So that is the resultant. A rifle fires a bullet of mass 0.020 kilogram vertically upwards through the air. As it leaves the rifle, the speed of the bullet is 350 meters per second. Calculate Roman 1, the kinetic energy of the bullet as it leaves the rifle. Once again, we have the formula. Kinetic energy is given by a half mv squared. So this will be a half times mass. Mass is 0.020, so 0.020 times v, which is 350, and that is squared. Using our calculator, a half, that is 0.5 times 0.020 times 350, and that is this 350 squared. 350 squared, that will give us that is 1225. As you can able to see, the values have been given into two significant figures, so this will be 1,200 joules into two significant figures. Now, the maximum possible height that the bullet can reach, the GPE gained should be equal to the kinetic energy lost, assuming that there is no air resistance or there is no work done against the air resistance, and there is no energy that is converted to the internal energy. So if that assumption holds, then GPE should be equal to kinetic energy. Kinetic energy is 1,200. GPE is mass, m. We are talking about the same body, so that is 0.02. Oh, by the way, sorry. GPE, just a reminder, GPE is calculated by mgh. So if GPE is equal to kinetic energy, that means that should be equal to mass, which is 0.02 times g. For this case, we'll use 10, and then times h, which we are looking for. So therefore, h will be given by 1,200 divided by 0.02 times 10. So that will be 1,200 divided by 0.2, and that is 6,000 meters. The actual height reached by the bullet is less than the value that has been calculated in A, Roman 1, Roman 2 above. That is, that means it will be less than 6,000 meters. Explain in terms of the forces acting on the bullet why this is so. Remember, when the bullet is moving upward, there are two forces that are acting on it. There are two main forces that are acting on it. One is air resistance. So the air resistance, which is acting downwards in the opposite direction to its motion. This adds to the gravitational force that is also acting downwards. So the resultant force, the air resistance added to the gravitational force, they tend to pull the object, the bullet downwards, and therefore it will not be able to reach the 6,000 meters. And that is why I said the assumption was that air resistance is ignored in calculating the maximum height. Roman 2, as the bullet rises through the air, its kinetic energy decreases. Why the kinetic energy decreases? One, kinetic energy decreases because it is converted to gravitational potential energy. And we have mentioned about the air resistance here. So that means some of the kinetic energy is also converted. Some of the kinetic energy is also converted to the thermal energy, or the internal energy, or it can just be together. Thermal energy we see related to the environment, and also the internal energy of the body. So that is how we respond to such question. There's another question here. A force is used to move an object from the Earth's surface to a greater height. Explain why the gravitational potential energy of the object increases. This is because there are variety of reasons which you can able to put here. Now, the one that is obvious is that as the object is rising or increases in, actually, as the object is rising from the Earth's surface, remember there is work done on it. So the work done on the object, there is work done by the force. There is work done by the force, or we can just say that this work done is equal to the gain in GPE, or the change in GPE. And GPE is given by mgh. So as the body is moving to a greater height, there is an increase in height, and therefore that means there's an increase in GPE. But B, the figure shows a train moving up towards the top of a mountain. The train transports 60 passengers, each of average mass of 65 kilograms, through a vertical height of 1,600 meters. Calculate the increase in the total GPE of the passengers. So GPE is given by mgh. There are 80 passengers, each of 65 kilograms. So that means the total mass will be 65 kilograms times 80. This is total mass. We multiply with g, which is 10, times the height to which they have been raised. That is 1,600. So that will be 65 times 80 times, that is 10 times 1,600. That will give me 83,200,000. So into two significant figures, that will be 8.3 times 10 power 7 joules. So that is the increase in GPE. Now, part C of the question, the engine of the train has a power of 1,500 kilowatts. The time taken to reach the top of the mountain is 30 minutes. Calculate the efficiency of the engine in raising the 80 passengers 1,600 meters to the top of the mountain. This question can be approached in two ways: if you want to use power, or if you want to use energy in calculating efficiency. So let's use let's define efficiency. Efficiency can be defined as useful energy over the total input energy into the system. So the useful energy is 8.3 times 10 power 7 joules, as we have calculated here. The input energy, as we know, energy is defined as power times time. So power here, that is 1,500 kilowatts. 1,500 kilowatts. Kilo here means 1,000, so that will be 3 zeros there. We multiply with the time, which is 30 minutes. So that is 30 times 60. We have to convert the minutes into seconds. That's why I'm multiplying with 60. So that will give me, that is equal to 2.7 times 10 power, this is 3,369 times 10 power 9 joules. So therefore, efficiency is given by 8.3 times 10 power 7 divided by 2.7 times 10 power 9. So 8.3 times 10 power 7. The answer. You're supposed to multiply this by 100%, or you can just give your answer as a fraction. So if you do that, that will be 3.1%. So it is only 3.1% efficient. Now, method 2, in terms of power, we can define efficiency. So efficiency can also be defined as useful power over the total input power times 100%, or you can just leave as a fraction or as a ratio, sorry. You can just multiply by 100%. Now, from the question, 1,500 kilowatts, that is the input power. We can therefore calculate, we can determine the useful power from here. So the useful power, remember, power is defined as energy per unit time. So energy, that is 8.3 times 10 power 7 divided by the time taken, that is 30 minutes. So 30 minutes we'll have to convert into seconds. So that is times 60. And so if you do that, that would be 8.3 times 7 times 10 power 7 divided by 30, that is 1,800. So we'll get that is 46,111. As you can able to see, you are not advised. You are not advised to round off the answer prematurely, before the final answer. So therefore, from here, efficiency is now defined as the useful power, that is 46,111 watts divided by the input power, which is 1,500,000 watts. We multiply with the 100%. So, and that still gives us, if we multiply with the 100%, that gives us 3.1%. Or you can just leave your answer as 0.031, just like a ratio.